something you're interested in, please look there. I will send it out in the next weekly email as I try, to tell you everything that's on there. So in case you didn't remember, I'll remind you. So we're going to start with some clicker questions today. The first clicker question is, which double bond will react first when presented with an electrophile? Choices being A, B, or both can react with ease. 41, always 41. I know they tell you what it is for the room computer, but a laptop is 41. All receivers they send out are 41. 41.
Yeah, we can't pull it off.
I haven't hit play. That's a new feature. Here we go. Now you can. Alrighty.
It can use both, right? It will react first. It's going to be A because it goes by like carbon.
We're going to go with 30 seconds here. Shouldn't take that long to figure this one out. I'll count down the last 5 with my 30.
But wouldn't it wouldn't it be like you could use residence to get to that structure? But I guess if you have to go through like the process of moving it over,
I always put the same way.
do you see what I'm saying? Like if you use residence and have it go on that one, then you can move it over.
2, 1, and we're going to stop the polling here. So 77% of you. Great. A. Perfect. Good start. Okay, here we go. Question 2. Go. I wish I could. I can name it for you, though. Would you like that?
This is going to be the kinetic product.
So this would be 3-methyl 2,4-hexadiene. So 3-methyl 2,4-hexadiene. And it's asking that you react it with 1 mole of HCl at minus 78 degrees Celsius first, and then react it with HBr. So again, 3-methyl 2,4-hexadiene. Reacting first with 1 mole of HCl at negative 78 degrees Celsius, followed by HBr. So a synthetic scheme. Step 1, isolate, bring it into reaction 2, add HBr, clean up your product. What is one expected product here?
I don't know. Kinetic. It doesn't.
It's the fastest. That means it's the one that's not. No, it's not more serious. Right. It's more like.
I know. I put 1.
Oh, right.
All right, we're going to go with about 1 minute here.
These substitute product. CL. It'll be 2. 2 or 4. Are you doing 2 or 4?
All right, we're about 10 seconds.
I have here. I'm checking my R and S.
4, 3, 2, 1, and we are going to right, so we're all over the map. The answer is 1, I think. Okay, but let's work through this. Clearly one we need to work through. And let's do that.
Can I tell you like
All right.
for this? This one forms a stable carbocation, that's what the fluorine would attach, and this one, the stereochemistry here, is that to attach it into there so it will that one. Think about where the hydrogen is going to
So we're looking at this reaction here.
The hydrogen
Yeah,
that's how you start numbering where's the hydrogen going to add.
Okay, so this is what we start with. You know what carbocation is going to form first because you already told me which alkene is going to react first, and you were all right. So when I add 1 mole of HCl, this is what I'm going to get in terms of a carbocation. Okay? So this is the carbocation that's going to yield initially. Now if I maintain my reaction conditions at -78, this carbocation is going to be the one captured by the nucleophile. So in terms of what happens in the second step of this mechanism, because I'm at -78, the nucleophile is going to attack this more stable carbocation. Okay? And -78 indicates that carbocation stability is running this reaction. Remember, anything that's room temperature above indicates that it's the less stable carbocation it's going to proceed through, because the end product stability is what dictates what product is going to come out of this reaction. So, not following stereochemistry, because you'll see how easy stereochemistry here is in a minute. This is what I would get from this reaction. The next question is, when adding HBr, clearly there's only one alkene present at this point, and I see that you see them as equally substituted, but we had a conversation, maybe a minor one, and conversation might not be what it was, might have been me telling you. So in this case, we're always going to form the carbocation that's furthest from the halogenated site. Okay? So there's 2 potential choices here of carbocations, this being one of them, and this being the other. Okay? This carbocation is more stable, the one on the bottom. Okay? It's more stable because the carbocation is furthest away from the already halogenated center. Okay? This is less stable because you have the ability for the Cl to draw electron density toward it, making this positive charge even more positive, right? So that's less stable. So you always want to choose the carbocation furthest from the halogen that's already on the molecule. So in this case then, as you continue through, this is the carbocation of choice. We're going to see attack here. Now the question about the stereochemistry, which clogs everything up and clogs everybody up every time we start with those R's and S's, right? Is that this is a carbocation center at both sites nucleophiles are attacking, right? It's a carbocation center, and a carbocation center can attack from the front or the back each time it attacks, which means I can get R or S stereochemistry out of this product, or after the first step. R or S can be garnered here. And as I take these, right, if I take a racemic mixture and I continue on, and I proceed through a carbocation intermediate, I could also get R or S from this center here. In essence, there are 2 new asymmetric carbons that are created through carbocation centers, which means I can get a racemate, right? RR, SS, RS, and SR. Generally 25% yield of each. That's theoretically. It obviously doesn't play out that way. You won't ever have to judge which one's going to be the dominant one. Okay? Yeah?
So what was the name again?
So this guy is 2-bromo, 4-chloro, 4-methyl-hexane. Right? So I'd have to, no, yeah, 2-bromo, yes. Okay, so you can check this out, but this is the process. Okay? Are there questions on the process on the board? Okay, great. So this is the type of question that you'd have to be able to answer, probably, I don't know, a 7 or 8 point question on an exam question. I mean, you won't ever have to name it to give the product, right? The naming is just a multiple choice piece, yeah.
So what was that stuff you saw in last class about, like, where the hydrogen atom as carbon 1?
Yes, so in terms of what product resulted from my reaction of dienes, okay? So this is my kinetic product, which is what I was alluding to when I said you're going to generate the kinetic product, because it's always going to flow through the more stable carbocations. But if I wanted to question what product this is it the 1,2 product or the 1,4 product? the electrophile added here, and I numbered through the double bond, right? So this, in essence, is the kinetic product or the 1,2 product. It is often that the 1,2 product is the kinetic product, not always, but often. And I did show you examples where the 1,2 product is not the kinetic product. So think through the example, but oftentimes 1,2 and kinetic align. Yeah?
The halogen is really far from the carbocation. Does that not have an effect?
Yeah, that's exactly right. So what the halogen does is it inductively draws electron density. And that induction really falls off after you're about 1 bond away. Okay? So this is a pretty hefty inductive effect because the carbocation is on the neighboring carbon, right? But this is 2 carbons removed, and that inductive effect almost falls off to 0. It's almost like that carbocation doesn't even know there's a halogen on the chain that far away. Okay? Yeah?
Will the HBr part of the reaction have a
Okay, the cold and the hot doesn't matter when we're talking about one alkene reacting. Cold and hot only applies when we're looking at a conjugated diene in its initial reaction with 1 mole of HX. So in this case, we go back to just the stuff we remember from last term, right? Which is generate the more stable carbocation intermediate and then proceed with nucleophilic attack there. The extra layer is to remember how that halogen that's already on the molecule affects carbocation stability. So I'm trying to get you guys to garner the carbocation that's further away from the halogen already placed onto my straight chain. Okay? Other questions? Yes?
When you name the final product, do you name it like normally or 1, 2, 1, 4?
You can name it, you don't, the 1, 2, 1, 4 is just a way to describe the reactivity, but you can name it normally and someone could say, oh, that's the 1, 2 product, right? There's all sorts of ways, those are generic ways, but the name itself, right, is what we would name the product if I were to put it in a jar and go sell it. Yeah? Yes, so this 1, 2 kinetic product, that language ends right here. Because it's right after we reacted the conjugated system that we use that language. When I move forward to my second reaction, this is nothing but an electrophilic addition reaction of just an alkene. It happens to be that the chain does have a halogen on it. But we no longer can use that language because there's no resonance involved. Yeah?
Why does that have to be 1 mole of HCl?
Okay, that's a description because if I added 2 moles of HCl, then really both double bonds are going to react. There's an order to that reactivity, but they would both react, right? So generally when we say HCl, that actually brings up a different question. So hold on just a second. When we say HCl, right, this is HCl that isn't like 1 molar. Like when you use HCl in the lab, you generally are using like 1 molar, 2 molar, something low, right? When you use concentrated HCl is what we use for these reactions. This concentration is like 17 molar. I mean, it's something really crazy. So if you add just a little bit, there's so many molecules of it that it in essence could react, right, with everything. Yeah. All right? That's another good tidbit. All righty then. So today we're here to talk about Diels Alder. So let's start talking about Diels Alder reactions. So let's start schematically with what just Diels Alder is, and major players and things we need to know about the major players. And then we'll start looking at the stereochemistry and regiochemistry of those reactions, starting simple and working up to the crazy ones. Okay, so most simplistically, Diels Alder is between a diene, and the diene is implied as conjugated. That should make sense because we're in a chapter that we're talking about conjugated dienes, right? So isolated dienes are not going to undergo Diels Alder. So a conjugated diene, of which the simplest one I can have is 1,3-butadiene, it definitely has one geometry that it must maintain or become in order to react. And this geometry is something that we call S-cis geometry. So the diene in a Diels Alder reaction, so this is all Diels Alder. These boards are made for really tall people. Okay, so the diene in a Diels Alder reaction must maintain something that we call an S-cis conformation. What that is saying the sigma bond that exists between the two conjugated alkenes must have a cis relationship of the two alkenes. Okay, so this is it. This is my sigma bond, and my two alkene units that flank that sigma bond are pointed to the same side. Okay, this here is what we would say S trans, right? That's a sigma bond whose two alkene units point to opposite sides. S trans molecules do not undergo Diels Alder reactions. The molecule, the diene, must be able to maintain or adjust to an S cis conformation. Okay? Certainly not the most stable conformation, I'll give you that hands down, but it must maintain that in order to react. Okay? So, the first thing you have to be able to do is rotate any diene given to you to the S cis conformation. Okay? Because they are generally given to you as they're normally written, you know, in ChemDraw or whatever. Okay? So there's always a reaction between the diene and then something we call the dienophile, which in essence means diene-loving, right? So it's between the diene and some diene-loving species. And this is generally just an alkene. Now I have the simplest alkene here. Be all sorts of things off of it in other directions, and we'll talk about that. But it is an alkene or a pi bond that reacts. Now, more often than not, we talk about CC pi bonds, but CO pi bonds can react, CN pi bonds can react. There's lots of other pi bonds that can react as the dienophile in a Diels Alder reaction. It's not as common, but it is a possibility, because the only requirement is that it be a pi bond. Okay? So, between a diene and a dienophile. Now, this is the simplest reaction that we can have, and it actually forms cyclohexene, and I'm going to show you how that happens. But this is the end of the reaction. This is exactly what you get when this exact diene and this exact dienophile react. Okay? So, what actually happens is you see this pi bond donating a bond to one end of the dienophile. It's going to utilize its pi bond to make a sigma bond to one carbon of the dienophile. Okay? That carbon of the dienophile has to do something. It has to reorganize, right? Because it can't take 5 bonds. It's got to get rid of one. So it takes its pi bond and offers it to the other end of the diene. Okay? So in essence, this diene and dienophile come together. The last bit is for this carbon to get rid of its 5th bond, it moves its pi bond down here. Okay? So your product is always a 6-membered ring. It's always a 6-membered ring, first and foremost. And the 6-membered ring will always have an alkene unit in it, and the alkene unit was once the sigma bond, right, of the diene. So you can orient yourself in a Diels Alder reaction by finding that alkene unit in the 6-membered ring that's created and recognize that that was once the sigma bond of the diene itself, which then allows you to map out the rest of the molecule. If this was the sigma bond, then this had to be one of the alkene units and this had to be the other alkene unit, right? Which means this is a new bond here and this is a new bond here, and I can now split, right, my diene and dienophile from each other. So you need to be able to work in one direction, and I'm trying to give you the strategies, right, the things you want to look for in order to work backwards, okay? So this is what we call a 4n+2 reaction, or a concerted reaction. It happens all at once. The only thing really needed to make this reaction a go is heat, okay? And how much heat is required really just depends on the system we're working with. Some systems require a little bit more heat and some require less heat, but generally they aren't going to go at all unless you apply some heat. Matter of fact, I could still remember right when I started teaching organic chemistry at a small college in New Jersey, the College of New Jersey if anyone's from New Jersey, which that's another interesting tidbit, but we'll tell that story a different time. And I was in the lab, because at a small college the instructor is in the class and then in the lab. And so I was in the lab, and one day some dodo, instead of getting out a, I can't even remember what it's called, like Variac, you know, you put the round bottom flask in them, and they sit nicely in the round bottom flask. Yeah. You can dial up the temperature, yeah. So most everyone has these variacs out, right? No, this dingbat went out and got a Bunsen burner. Big problem, right? Doing a Diels Alder reaction, need heat, had the Bunsen burner's going, flames. Oh my God, fire in the hood. They're like, Dr. Dixon, there's a fire! And I'm like, holy hell, how could there be a fire? Like who, what is someone smoking? I mean, I was so distraught. But here's the bottom line is when I get really worked up, like, and you won't see that very often, but when I get really worked up, I talk out loud. So I was like, oh my God, where's the fire extinguisher? I don't know where the fire extinguisher is. The whole time out loud, right? I don't know how to use a fire extinguisher. I've never used a fire extinguisher. Still out loud, right? No thought to stop it. How do I get the tag out? How do I get the tag out? The whole thing, right? And so the students continue to like back away and back away and got the fire out, right? And they were like, Dr. Dixon, we were really worried. They were. You just did not know. So I can now use a fire extinguisher. We're all safe. I don't know where it is in this room, but I know how to use it. Anyway, it does require heat. Don't ever use a Bunsen burner, okay? That's the bottom line. So you do need heat for this reaction to go. Yes?
With regard to the conformations for the cis and tran, doesn't a sigma bond have free rotation? So in any given, isn't it like 50% trans, 50%
That's a
cis?
great question. So I can come up with, say, this guy, or alternatively, this one. These are constitutional isomers of one another. One of them will react with a Diels Alder reaction and one won't. Which one's going to react?
Right.
Right, and the one on the left cannot, right? So not everything has, most things do, but not everything does. So this is sort of the trick of the trick question, which will show up on clickers at some point, but now you'll get it right. Okay? Are there any other questions before we get going? Okay, so to make the reaction go faster, there are some things that we do to the diene and the dienophile. Okay, and that actually adds some complexity to the situation. So, one thing we do with the diene, which we know, and actually, this truthfully, I'm going to talk about this all as like a resonance piece, but truthfully, it all has a molecular orbital basis. Okay, I tried to tell you online last Friday about how molecular orbital theory and resonance sort of speak to the same thing. I went through a whole thing with the 1,3 butadiene, and I was saying that if I looked at the two bonding molecular orbitals, the two bonding molecular orbitals that I had, one was all overlap, right? And one was a place where, and I'll just dot them here, where I could have so one is all overlap, which in essence is saying I can run across this whole thing, and the other pi molecular orbital had a node that went right through here, right? And it was saying I can have electron density here, and I can have electron density here, but none is going to be found here. And we used resonance as an argument, right? We said there's a weighted average to the resonance. All of what I'm about to say bears out in molecular orbital theory. If you're really interested and you want to one-up yourself, you really can look at this as a homo-lumo overlap and understand how these substituents change the energies of the homo-lumo gap. And that's actually the real answer to what I'm about to say, and I'll be using colloquially just resonance to make these arguments. Okay? So in order to make the argument, we have to agree, and you'll just have to agree, I think, just flat out, we have to agree that the diene is what runs the reaction. Okay? The diene is actually, in essence, the nucleophile in the reaction. Now, if you don't want to believe that, certainly I can tell you that there are two types of groups that I can put on anything. We're going to take a benzene ring here as our example. Okay? One of them we would call an electron donating group, and one of them is an electron withdrawing group. And Caitlin will be talking about this next week, so you will definitely see this again. This is actually really important to understanding aromatic chemistry. But we do need to specifically understand the difference between what I'd say is a donating group and a withdrawing group. So this is generically what we would say is an EDG. That's how we classify it. That's how we, has the acronym for it. So this is electron donating group, okay? And this here is an EWG, which is an electron withdrawing group, okay? Now what makes this OH, because the OH is specifically what I'm calling a donating group, okay? okay, a donating group. And what makes this carbonyl, this aldehyde, a withdrawing group is as follows. Okay? Most generically, a donating group will be an attached atom that has electron pairs. Okay? An attached atom to your system, our system that we're looking at here on the board, to explain the donating group, will have electron pairs, which means through resonance, it can donate electron density into the ring. That's what you do for resonance structures, right? You'd always start an electron pair, and you'd say, okay, I am going to generate my first resonance structure, and my first resonance structure will look like this, and hence it shows that my ring is becoming more nucleophilic, right? It's becoming more negative, a better nucleophile, right? Because I'm donating electron density into it. This over here is a withdrawing group, most classically because of this. If I look at the directly attached atom to the system, okay, it is actually an atom that is sp2 or sp hybridized, and generally it's also involved in a bond to an electronegative atom. So usually there's two classifications here. It's sp2 or sp hybridized, that fits, it's sp2, and it's bonded to an electronegative atom, oxygen, okay? And what this type of group does is it pulls out electron density, right? So it's going to, in essence, pull out electron density, and if I draw its one resonance structure here, it's going to look something like this, where now the ring has become less nucleophilic. The system has become less nucleophilic, okay? So we use this language. Electron donating groups make the system we're looking at more nucleophilic, okay? Again, those are generally things that have the directly attached atoms with electron pairs. So you can imagine alcohols and amines, and amides if they're attached to the nitrogen. You see what I'm saying? Esters if they're attached to the oxygen, and sort of make classifications. And electron withdrawing groups make the system we're studying less nucleophilic. And there's two sort of generics about those. First, they're sp or sp2 hybridized, the directly attached atom to the system. And second, they're generally involved in a bond to an electronegative atom. Oxygen counts. Okay? So, I know that the diene is the nucleophile because studies show that when I stick electron donating groups on the diene, the reaction runs faster. But if I stick electron withdrawing groups on the diene, the reaction runs slower. Okay? Let's take that out. It says, if I put electron donating groups on the diene, my Diels Alder reaction is faster. And correspondingly, when I stick electron withdrawing groups on the diene, my Diels Alder reaction is slower. So this evidence, based on reaction rate, tells me that the diene is what's doing the initial pass of electron density in my pericyclic concerted reaction. Okay? So we know that dienes prefer electron donating groups. And there are lots of choices for electron donating groups, and you'll see lots of examples as we move through this. Okay? Generally, one electron donating group is enough to really make the reaction go fast enough that it's of utility to us in a lab environment. Okay? The other piece is from the dienophile. Now, I can take the same knowledge. I can say that an electron donating group on the dienophile makes the reaction slower. Whereas, evidence shows that I put an electron withdrawing group on the dienophile, the reaction is faster. Okay, so this tells me that the dienophile, in essence, is serving as the electrophile in this reaction. It's capturing the electron density that's donated from the diene, and that's the spark for the reaction. Because all reactions occur when a nucleophile seeks out an electrophile. That's the spark for any given reaction. So we know then that we want electron withdrawing groups on the dienophile. So your typical Diels Alder reaction will have a diene with an electron donating group and a dienophile with an electron withdrawing group. Okay? You can have more than one, but your typical one is to do that. So let's start and think through that process. Let's make a Diels Alder reaction that we know is going to run real well. We can start with, say, something. So here is a reaction. Generally can identify them in the reaction sequence of a reaction scheme or on the reaction page of an exam because there'll be only heat below the arrow. That's a sure sign that you have a Diels Alder reaction. So be looking for your diene and your dienophile and making those considerations. Now, certainly this has a regiochemistry piece to it, okay? Meaning, which way are these going to align? I have it drawn diagrammatically one way, but who's to say that the reaction can't occur like this? Because I would get two different products if I ran the reaction the way I initially drew it, which just was happenstance that I drew it that way, or if I ran it like this, okay? So everyone see that I get two different regiochemistries. I would name my molecules two different things. They'd be constitutional isomers of one another. So the question is, which one is the right one, okay? What I can tell you is, and I think it's just happenstance is that I always draw them the way that I know the product's going to be. I think it's just from doing it so many years. But generally, you get these 1,4 products, where the substituents are sort of opposite ends of the molecule. But there is a way to think through this process. So let's pause and take a minute and think about what the ways are to work through this process. It does require resonance. And this is a place where we can ask you to draw resonance on an exam. And you likely will be asked to draw resonance on an exam. So the question is, can you draw the resonance structures of each one of these reacting species? Okay? So see if you can work through with me. The resonance structure here would have to start on the oxygen. Okay, right? We always start with the atom of the electron pair. And I donate electron density down, and that atom can accept this pi bond because it's sp2 or sp hybridized. It's going to have to relinquish or give up a pi bond, right, to its atom. So this is the arrow formalism that I would use to generate the resonance structure for this molecule. So the resonance structure is one that looks like this. So where is my nucleophilic atom? I'm going to asterisk it, right? It's right here. This is my nucleophilic atom in the diene, right? That's my nucleophilic atom. So that's going to be starting the reaction, right? Because it always is nucleophile seeking out electrophile. So I come over here, and I'm going to draw the resonance structure for this guy. And we know that's an electron withdrawing group. So I know that it's going to pull electron density away from the diene, okay? So we're going to generate something like this. You can certainly pass electron density between these two oxygens, but that's not going to help you understand what's going on in the dienophile here. So in this case, my resonance structure looks like this. So where is my electrophilic atom? Where the positive charge is, right? So if I take that information that I get from resonance, and I just put it back onto the original molecules, I can see, erasing the resonance arrows here, I can see that this is my nucleophilic end, and this is my electrophilic end, and hence this is where the reaction is going to start. I must have this orientation. I would never have this attacking, how would you say that? This, like you would have over here if we kept it the way that it was on this side of the board, I wouldn't have it do something like that. Okay? It has to pass to the top. Okay? So it's top to top, bottom to bottom. You never have a cross from top to bottom. Okay? So in order to maintain nucleophilic attack at the precise electrophilic center, top to top or bottom to bottom, just neighboring, this is indeed what's going to happen. Okay? I'll see nucleophilic attack at electrophilic center, and then the resulting pass of electron density. So what I get out of this reaction then is this product here. And it is true that generally the substituents are farther apart, not closer together. Yeah?
So do you mean that the top part of the die
Yes. So I'm saying that,
needs to be open?
yep, so the attack's always going to be to make a bond top to top, not top to bottom.
Okay. So that part with the efflux always needs to be open?
Yes. Yep. Okay? Does everyone see that? Yeah.
If the diene was a benzene ring, would that be slower because the double bonds are an electron withdrawing group?
Oh, that's a
faster to get locked?
great question. Yes, much slower. Benzene is slow to react because of the aromaticity, which is the unit that Caitlin's going to be picking up next week when we talk about aromaticity. Yes?
Is it also a reason that you're using this for the product that happens because it's more stable this way, but hopefully this will have it.
Okay, in some cases, yeah, I mean, that's not a bad reasoning. In some cases, though, some functional groups prefer to be closer together. There's all these random examples of like diols. Like diols create these crazy structures that you wouldn't expect ever because of the hydrogen bonding that can exist. So sometimes it's, you know, you have to analyze each situation separately, but yeah, that is not a bad guess at all, right? Sterics would definitely dictate this. Okay, so what do we think the stereochemistry is around this asymmetric carbon that was created? That is an asymmetric carbon, not in the original molecules, right? That was created through the stereochemistry is here. R or S? Is that random? You like R better? Oh, you mean because it looks right now R? Well, that's, I mean, we don't need a wedge or a dash, but I mean, what do we think? What would theory dictate to us? Okay, the dictating here would be that this could be R or S, okay? And that's true. You can have R or S stereochemistry because the way these react, right, is they can react this way or they can react this way. Okay, so since they can react either way as they sit on top of one another, you actually can get both R and S stereochemistry here. Okay? That make sense? Okay. Let's stay in the stereochemistry vein here for a minute before because I usually like to close with the crazy because you guys all just go crazy over the crazy. So, in the stereochemistry vein here, let's go back to our simple diene and dienophile over here, because we're putting in all sorts of things that we can know about them. And here is another thing that I know. Okay? When I react to diene and a dienophile, and I'm going to be generic at first, these positions that I've marked with A will be on the same side in the product, meaning both wedges or both dashes. These here are marked with B will be on the same side in the product. And any relationships from the dienophile will be maintained. Okay? So let's generate this product just as a generic here. Okay, so here I go. A's will be on the same side, which means they both have to be in wedges or both dashes. They will always be on the same side. If they are pointed up completely or down completely in your S-cis conformation, they will be in the same symbolism in the Diels Alder adduct. That's what we call this guy. This is a Diels Alder adduct, not adduct, adduct, UCT. Okay? So that means then that anything points internal to the cave that's created in the S-cis conformation, internal will be on the same side. So both wedges or both dashes. Both are probable, right? You can have both wedges or both dashes, but the A's have to be sharing the same symbolism and the B's have to be sharing the same symbolism. You can switch the symbolism they're sharing, but they have to share the same symbolism. Okay? Just like out here, the C's will be on the same side and the D's will be on the same side. Okay? That one's a little bit more obvious, right? Because if they're on the same side in the original dienophile, they will maintain that when we get to the Diels Alder adduct. Okay? It's a little crazy, right? But this is the stereochemical result from these reactions. So let's look at one of those really quick and see if you can't draw for me what you get for a Diels Alder adduct here. I'm going to put this on the weekly quiz, this problem right here. So it'll be the first problem on the weekly quiz. I'm going with what we have diagrammatically here to stick to stereochemistry. I want you to think through the regiochemistry of this problem. Okay? So it's going to be the first one on the weekly quiz, which is just the problem set to try. Okay. So if I heat this up, I know that I'm going to get the six-membered ring. I just always start with that as a framework, because I know that's exactly what I'm going to get. So I map atoms, and I know that this nitrogen, this atom here, will have that NH2 group on it, and then the methyl group will be in the opposite symbolism. That makes sense, because you have to have a sp3 center, one wedge, one dash, two bonds on the plane of the page. The question is, where is this group going to go off of, the fourth carbon of my diene? And that's going to have to go into a dash here, right? Because it has to share the same side as the methyl group from carbon 1, the carbon the nitrogen is attached to. Okay? Question of where these two groups go with respect to one another is they can both be wedges or both be dashes. They just have to share the same symbolism. They're both probable. So we can just be dashes just as a sort of a guess. Okay? So this is one probable stereoisomer that results from this reaction. Okay? It's not the only one, it's just possible. Okay? Yeah?
Can you point out the nucleophilic carbon and the electrophilic carbon?
Okay, that's what you're going to do. Yeah. On the weekly quiz. Okay. Very good. So this is the stereochemistry piece. It's an annoyance, but it is important. Yes? I'm listening to you.
Do the A and B correlate with C at all?
No, they don't generally. There's some hindrance involved sometimes, but you're not going to have to get into that. You're never going to be asked to judge that. Okay, so the last piece is what happens when you create what we would say is a bicyclic system. A bicyclic system. So that is when one of your materials is already in a ring. So let's start with, say, this guy here. So if my diene is already part of a ring, what do you get as the Diels Alder adduct when you react that? So say I take this and I react it with something like this. Okay? And I heat these two things up. Okay? This is actually what you get.
What?
put this right in the chair comforter?
The chair comforter. This isn't a chair comforter.
I forgot the name, but like, there's a other way to draw this, but that's
Like,
a fancy way of doing it.
Yeah, this is the three-dimensional way. Yeah, we should be able to do this. I think we can do this. Yeah. I know. Yeah.
Would you mind just dotting
I'm
where
gonna
the?
map them.
Okay,
Yeah.
sweet.
You want to just draw it first, and then I'll map it for you. Draw what you see. Okay? So I started by doing
don't know.
this. I made my 4 of the diene, and then I connected my bridge. Start again. So I connect the dots, right? 1, 2, 3. You with me? And then your bridge. Down, down, attach. Okay? That's what it looks like. All right, try your best. Let me map them for you. You ready? This is 1, 2, 3, 4, 5 of the diene. So these go as 1, 2, 3, 4, 5. Okay? That's a correlated numbering system. Okay? Number for nomenclature, but also for the positioning in the Diels Alder adduct. And then we can number maybe these with primes. So this is 1 prime and 2 prime. So this is 1 prime and 2 prime. Okay? Now to start with, there are 2 potential products here. Only one is the one we get. So you could think that there are 2 potential sort of stereochemistries of where this carbonyl attachment's going to be. One is what we call endo, that's this guy, and this is pointed directly down, kind of like axial on a ring, on a chair comforter, but it's pointed directly down, okay? This guy is sort of off, and I guess you can say equatorial in some cases, right? This is what we would call the exo product. The exo product never forms, okay? The exo product never forms. So you have to get used to first drawing the endo product. And the endo product is the preferred one because this pi bond sits. It doesn't seem like it because the system, is spread out to draw it on the board diagrammatically. But this pi bond sits directly below this pi bond, and there's something called pi stacking. The pi stacking is actually what makes the endo product, the preferred product, a huge preference, like 90+%, okay? Almost always. So we're going to draw endo products. Now this system is what we call a bicyclic system, and we're going to learn, I guess, to name these bicyclic systems next class. There's something I want to say about the homework. The homework isn't going to be released till tomorrow morning. I'm actually not going to have it due until next Tuesday at 10 a.m. in my office, okay? All right? So if you can get it to me by then, that allows you still to ask me questions on Friday and Monday. Find me and ask me questions, and we're going to have it due Tuesday, okay? If there's any issue with that, you can come talk to me. I'll work with you. But this way we can get through more of Diels Alder on Friday and make the homework better for your exam prep.